Okay, class, so today we will consider PI control, and here is our PI control law, where we have our P action. So this is our P term right here. This is our P action, and then our I action is right here. So the action is proportional to the integral of the error, and I exploited the fact that I could use whatever I want for the dummy variable, and I made a dummy variable, an apple tree. Just note that, yeah, this is a dummy variable. So here's our I action. And the U here is the manipulated variable, right? So this is the manipulated variable or controller output. We're abstracting them to be the same here. So this is the manipulated variable. Controller output. And that's because we're considering our simplified closed loop block diagram down here, where we only have our process, and the PI controller directly outputs the manipulated variable. Okay, so the point of this lecture is to teach you about the smart and busy operator PI controller settings. You might have wondered by now, how do we determine a good controller setting? So the controller gain and the integral time constant, right? So this is the controller gain. These are the two parameters that we can choose. And this is the time constant, this tau I. Right, so these are two tunable parameters, and the idea is that we want to choose these to achieve good set point tracking and to achieve good disturbance rejection. So to come up with some good parameters, let's consider what a smart and busy operator would do to achieve a set point change. So we'll draw our smart operator here. All right, and this operator has very long arms, and they can reach over and change the manipulated variable, okay? So this is our smart operator. And they're very busy too. And our process here is affected by this manipulated variable. So this is our manipulated variable right here. Apologies, I have allergies. Okay, so the manipulated variable goes on and affects the process and affects the controlled variable y, right? So this is our controlled variable. This is the controlled variable. Well, let's use a different color for that. Let's use green. So this is our controlled variable. So it's a very simple setup here. All right, so the operator is able to adjust that manipulated variable. For example, he or she could open or close a valve to adjust the flow rate. So U could be a flow rate. And the operator knows the gain K, okay? So this gain K is known by the operator. The operator knows the gain of the process. And the goal of the operator is to adjust U in order to achieve a set point change of My, okay? So we'll make our set point change, we'll make this color green. So this is Y at its steady state value, right? So this is Y equals Y bar, which implies Y star equals 0, because Y star is Y minus Y bar, right? The steady state value. So Y is resting at a steady state value, and then we want to make a set point change. So this is the set point change, okay? So this value here is M sub Y, okay? So it's the magnitude, or it has a sign, so it could be negative, so I won't say magnitude, but it's the size of the set point change we want to make. So this is My. That's the goal. We want to achieve a set point change, and we can do that by adjusting the manipulated variable. However, the operator is very busy. He or she can't sit there and keep adjusting the manipulated variable. What they want to do is instead adjust the manipulated variable once and then walk away. So it's basically opening the control valve or opening a valve to a new setting or closing it a little bit more and walking away. So make a single adjustment. And in practice, what that really is, from a modeling standpoint, is a step, right? So I'll use blue because that's what we're using for the manipulated variable. Again, what the operator is going to do is U is at U bar, right? Initially, that's why Y is at its steady state value. So U star equals 0. And then the operator will make a step change in U, right? And that's akin to opening the valve a little bit more and walking away, right? And let's let this be M sub U. So it's the size of the change that we make in the manipulated variable. MU. So this is MU. That's the new value of U star. It's the magnitude of the change in U. Okay? And also, the operator is smart in that they know, since they know the process gain, they took CHE361, and they can determine exactly what value of MU they should set the manipulated variable at, okay? And so it's easy to see if we work backwards, because we know that if we have a step input to a first order process, okay, this manipulated variable is a step input, of M sub U, okay, that's a step input. That's what they do. They make a step input because they're busy. They just want to make one change and walk away. They don't want to keep adjusting it. If you make a step input, then eventually the new steady state value is going to be the gain of the process K, which the operator knows, times MU, right? So this is the gain of the process, right? Process gain. And this is the magnitude of the set point of the manipulated variable change. This is the manipulated variable step. Step size. Right? And what we want is for Y to eventually tend towards its new set point, right? We want limit as t goes to infinity, Y star of t, to be equal to M sub Y, so that Y reaches its set point, okay? And so, since the smart operator took CHE361, he or she would set My equal to K MU, and then solve for what MU should be. So then MU equals My over K. And voila, that's exactly the magnitude of the step that the smart and busy operator would make in order to achieve this set point change, okay? So that's the answer. That's what they should make. And then if they make a step change in the manipulated variable of that size, Y will eventually tend towards this new set point, okay? So I'll highlight that. That's the answer. That's the set point change, or the manipulated variable change that they should make in order to achieve that set point, okay? And now the question is, what does the response look like as a function of time? Of course, it takes time for the manipulated variable U to affect Y, right? So it's not going to immediately jump up. It will have some dynamics. And again, we can use our CHE361 principles to figure this out. So if we made a step in U, then this is the Laplace transform of that step. And Y star, well, we know that it's the transfer function times the input, right? And so this is equal to k over tau s plus 1 times m sub u over s, right? And in CHE 361, we derive this. In the time domain, if you invert that, you do partial fraction expansion. What you get is mu times k 1 minus e to the minus t over tau. So this is a first order response, right? All right, and so if mu, if we set it to be my over k, you can see that k cancels, right? And then what you'll see is that y star tends towards a set point in a first order manner. This is my 1 minus e to the minus t over tau, right? So what we'll see, and we'll make the set point here. So this is our set point. So this is m sub y, the set point, right? Maybe I should make it a different color because I want y to be green here. So this is a set point here. M sub y. Okay, and then what happens is it reaches that set point with first order dynamics, okay? And so, let's see, 63% of the new steady state value is about right here. And this is tau, the time constant of the process. So, of course, the dynamics respond with the time constant of the process, tau. So this is really CHE 361 stuff, but we used it to figure out what change in u we should make. And so over here, we should put a smiley face because we're happy that the step in u of size mu, which equals m sub y over k, results in y star reaching its new set point. Whoops, yeah, it's new, reaching its set point. So y star goes to my as t goes to infinity, right? With first order dynamics. Okay, time constant tau, okay? So the operator is smart because they took CHE 361, they knew the gain of the process, and appropriately made that change and manipulate variable. And they're busy in that they want to make the change and walk away, so it's a step, as opposed to continually adjusting it over time, because then they have to stay there and look at the controlled variable and keep messing with the valve. But they have other things to do. They're busy. Okay, so my claim now is that there are PI controller settings such that the PI controller will do exactly the same as a smart operator, okay? So first, let's get the closed loop servo response, the closed loop transfer function here. And note that we can write GC of S in a slightly different way here. KC. So 1 is really tau IS over tau I, right? So we could write it like this to simplify it. All over tau IS. Right? So that's another way of writing GC of S, right? So maybe I'll put this over here, yeah. So this makes the math a bit nicer. So we could write y star equals, and if we focus on this right here, it's GU times U. But U, if we focus on this, is GC times E, right? Okay. But E is a set point minus Y, right? And this is just a sort of review of your closed loop block diagram algebra. And if we solve for Y, what we get is Y star over Y set point star equals GU GC. And I'm going to call this GOL for G open loop. 1 plus GOLS, where GOL, which OL stands for open loop, is a product of the process transfer function and the controller transfer function. So this OL stands for open loop. Oops. The reason it's called an open loop transfer function is because what it does is it relates. So you imagine opening the loop, opening a comparator right here, right? And what the open loop transfer function does is it relates what you feed in the comparator to the error, right? Because this is equal to, so consider the output is Y star over E, right? So consider the error as an input, and then whatever comes right here, which is Y, it's really Ym in general, but here is Ym is the same as Y, right, the measurement. So that's why it's called an open loop transfer function. Imagine opening up this comparator right here, and then relating what goes into the comparator to the error signal. That's the open loop transfer function. And you always see a 1 plus G open loop in the bottom. Okay. Open loop transfer function. So we can write what the open loop transfer function is here. So here, G open loop of S is equal to GC times GU, and I'll simplify that a bit. So we'll get KCK tau I S plus 1 over tau S plus 1, yeah. And then over, and we have a tau IS as well. And so that's why it's a bit easier to write GC like this, because then you have GC right there. Okay. So, so just to show you here, I'll make this purple, right? So GC, whoops. So GC is purple, okay? And then we have our KC. We have a tau IS plus 1 and a tau IS, so that comes from the controller transfer function. And we'll make GU be orange. And then we have our K over tau S1. So that's GC times GU, right? So here's our GU. And here's our GC, okay? Okay. So a really nice simplification happens if we set tau I equals tau, the same, i.e. set the integral time constant equal to the process time constant. And the reason that we do that is because we'll see that we'll get first order dynamics and the closed loop response, just like the smart and busy operator controller. So if we do this, what we see is a pole zero cancellation. In G open loop. So it simplifies, right? So basically what happens is this cancels with this. So cancels if tau I is set to be equal to tau, okay? Okay, and so what happens is G open loop, those two terms then cancel. It becomes KC times K over tau is, and tau I are equal, so we could just as easily write kck over tau s. Okay, and if that's your G-open loop transfer function, closed loop response is, we can use this, substitute it into y over y star. So G open loop over 1 plus G open loop then is KCK over 1 plus KCK over tau s. And the set point here, the set point change is my, right? So this is my over s. So I'll make a note. This is the set point change. Right? It's a step. And this is your closed loop transfer function right here. So that's your closed loop response. And we can simplify that. Let's write this in standard gain time constant form. So first, what we can do is multiply by s here to get rid of the s in the denominator, right? S times that, and s times that, okay? Okay, and if we do that, we get KCK over tau over s plus KCK over tau times my over s, which again is not exactly ideal. So what we'd like to do to get that in standard gain time constant form and make this a 1, we would also want to multiply by tau over KCK. Multiply by 1 in the fancy way to get it in standard gain time constant form, right? So then if we do that, these become 1s. Right, so this will be tau over KCK s plus 1 and then we have our a 1 up here. Yeah. So this is the closed loop response as a result of setting the integral time constant equal to the process time constant. So this is a smart operator PI controller setting. So let's compare this to the smart operator, right? So here's the smart operator right here. So the smart operator controller responds with first order dynamics with time constant tau. All right, so here's our tau. We can get the exact same response if we set KCK equals 1, okay? So KCK equals 1, which means that the controller gain is 1 over K. And that is the second smart operator PI controller setting. So if KCK equals 1, what that implies is y star then equals m set point, my over s times tau s plus 1, right? And this is exactly the same as the smart operator response if you scroll up. So K times mu, let me delete this. K times mu is equal to my, right? In the smart operator setting. And so the smart operator response, so I'll label this is the smart operator closed loop response. And what I've just shown is that if you set tau I equal tau, kc equals 1 over k, you get exactly the same as the smart operator response. All right, so what we can do is replace the smart operator with a PI controller, and it will do exactly the same thing for a first order process. Isn't that great? I think that's quite intuitive, and we'll see a simulation down below. So what I've just done is argue that with these two controller settings, so these are the smart busy operator PI control settings. So if we approximate a process as first order, we know its gain and time constant. We can set our controller parameters as follows, and the PI controller will behave exactly as a smart operator. Okay? That's what I've shown here mathematically. All right, so one way to measure the performance of the controller, so this is the integral of the square error. You take the error signal, E, you square it, and you integrate it over time from 0 to infinity, okay, or whatever time you're interested in. You have to square it because if you don't square it, what you'd be doing is adding up positive and negative values, and then it could be 0, even though you have wildly oscillating errors. So this is a functional. So it's not a function, it's a functional because it maps a function, your error signal, into a single value, the integral of the square error, okay? So if you take a calculus, a variations class, it's all about optimizing functionals. In the control theory literature, you'll see people trying to choose control schemes that optimize this functional. So what this really is a metric for controller performance. And it applies to both servo, set point tracking, and disturbance rejection, right? Because we want the error to be 0. And it's large if the error is large for a long time. And we can calculate analytically what the ISE is for a smart operator controller, okay? So for a smart operator controller, ISE equals integral 0 to infinity, and the error is a set point minus y star, right? And we have an expression for y star above, right? It's integral from 0 to infinity. So we know what the response is, right? Y star t, this is a closed loop response. Yeah, so y star t equals my. 1 minus e to the minus t over tau. So this is the closed loop response. So I should say closed loop response of PI controller with Kc set to 1 over k, tau I set to tau, is equivalent to smart operator adjusting U. Okay, and this is the response. It's the same as what we derived above for the smart operator. So we can plug that in for this y star, right? And we get my. The ones cancel. You get e to the minus t over tau dt. But we have to square that, right? So this is squared. All right, and that's integral from 0 to infinity. M sub y squared e to the minus 2t over tau dt. Okay, continue down here. This is a simple calculus exercise. My. And then we have a minus 2 over tau e to the minus 2t over tau. Right, because if you differentiate that, well, this should be tau over 2, right? Because if you differentiate it, that will cancel. Yeah, so this will be tau over 2. Evaluated from 0 to infinity. So the infinity term goes to 0. And what this equals is my. This is squared. My squared tau over 2. Yeah, so we can calculate this analytically. So what this tells us is large tau, large time constant of the process. Those are slow process dynamics. Then we have a larger ISE, and that makes sense because it takes a longer time for the process to respond to the change in a manipulated variable, the step change, and for y to reach its set point based on that step input. So it's sort of nice that we can calculate ISE analytically for the smart operator, and we get an intuitive result. Okay, so in summary, the smart and busy operator controller settings are as follows. They're highlighted in red there. And they pertain to approximating your process as a first-order process. And upon a set point change of y, it results in an automatic step change of magnitude mu, which is your set point change divided by the time or the process gain in a manipulated variable. And also upon the set point change, the controlled variable, the PI controller makes it reach its new set point with no steady state offset and with first order dynamics, and those dynamics have the same time constant as the process itself, okay? And we'll see this in the simulation below. And as a remark, this is a conservative controller setting for your PI controller, but we can make it more aggressive by setting Kc greater than 1 over K. So we can make the PI controller more aggressive by bumping up the controller gain, okay? And then the first order response is faster, and we can see that right here. See that? So if we increase Kc, then what will happen is the time constant of the closed loop response, which is this whole thing, is going to go down, right? So that means it will have a faster closed loop response, and it will still be first order. However, you have to be careful in doing that. The reason is that having a large controller gain, as we discussed before, can lead to large oscillations and controller instability, and we'll show that mathematically later. And the reason is that we're neglecting higher order dynamics and time delays, which are always present in a real process. So not all processes are first order. And I should mention that even though this pertains to approximating your process as first order, we can always approximate, well, not always, but usually we can approximate real processes as first order, even though they're not. And this is still a great heuristic for determining PI control settings. Okay, and you'll do that in your studio later. So I just wanted to show you a simulation finally. So now You'll note what I've done is I've made KC equal to 1 over K. So that's your controller gain. And I made tau I equal to tau. Okay, so this is the same K of your process, same tau as your process. And I've simulated a set point change of my, which is right here. All right, so the black line shows the set point change that I made. And of course, y can't immediately jump up there because it takes a while for the manipulated variable to take action. But when you tell the controller that you want to change the set point, what happens is, miraculously, well, it's not miraculous anymore because we've gone through the math, but this is your controller output. So this is your controlled variable right here. Controlled variable. This is your manipulated variable or controller output. And we should use the same colors that we used above, right? So control variable is green, right? So we'll change this to green, okay? And the manipulated variable is blue. And this is the controller output. Okay, and what we found is that this PI controller, even though there is no operator there, it behaves exactly as our smart and busy operator. What it does is it makes a step input in the manipulated variable. And let me move this here. The size of this step change, m sub u, is equal to m sub y over k, as we can see from up here. Yep, mu is m sub y over k. And it did that by making the P action and I action, which I plotted separately here, add up to be the step input, okay? So this is sort of a flavor of artificial intelligence, right? Because you told your controller that you want a set point change of my, and with these PI controller settings, it behaved exactly as that smart and busy operator, making a step change in the manipulated variable of the appropriate amount in order for y to reach this new set point. So I think this is pretty neat. And it's very practical too, because it gives you a good starting point for conservative PI controller settings, and then you can make your controller more aggressive from there.